Okay, we're going to continue with the gas laws. This is the fourth video for chapter 12. And we're going to start with Avogadro's law. You might remember Avogadro. He had defined what a mole was. So he said that a mole was 6.022 times 10 to the 23rd of anything. So Avogadro's law is actually going to deal with the amount of molecules in a gas, because Avogadro liked the mole. What Avogadro's law basically says is the moles of a gas are proportional to its volume if you hold the pressure and temperature constant. So if pressure and temperature are held constant, the moles of the gas are proportional to the volume. What does that mean? Well, this kind of makes sense. This is one of those nah-duh laws. If you have 1 mole of gas, let's say that you have a sack, and you tie it up and it's got 6.022 times 10 to the 23rd particles in it, a mole of gas. So 1 mole of gas will occupy a certain amount of volume. What happens if you add a second mole of that gas? And I can't even draw symmetrically. If you add another mole of that gas at the same pressure and temperature, then isn't it going to be at the same volume too? Yeah. So 1 mole of gas will occupy a certain volume. If you increase the moles, if you have 2 moles of gas, don't you have twice the amount of volume? Yeah. What Avogadro's law basically says is, as you increase the number of moles of gas, you proportionally increase the gas's volume, holding pressure and temperature constant. Now we can draw something else from this relationship though. If you have 2 different gases, and they're at the same temperature and pressure, if they contain the same number of molecules, then they will be at equal volumes. What in the world do I mean by this? Alright, let's say I have 2 gases here. Let's say I have hydrogen gas, and I have chlorine gas. Now we know that they weigh different amounts. They have different molar masses. But if I have hydrogen gas and chlorine gas, if I have the same volume of those gases, I'm not going to, well, okay, I'll draw the cube. I feel like I need to draw the volume versus the three-dimensional shape. Alright, so if I have the same volume of the gases, so the volume's the same, if I hold their pressures the same, let's say they're both at STP, so standard temperature and pressure, if they have the same volume, the same pressure and temperature, then that means I have the same number of moles of each gas. Another way to say this, if I have the same gas at standard temperature and pressure, and they have the same number of moles, they will occupy the same volume. Okay, so any 2 gases that have the same volume will contain the same number of molecules. So let's say you're storing a whole bunch of gases at standard temperature and pressure in the same volume tanks. And they're at the same temperature, the same pressure, same volume. They have the same number of moles. Alright, now let's come down here. I'm just going to skip down here because I kind of said all that. That's stuff you can do. Let's look at something called molar volume now, because Avogadro defined something called the molar volume of a gas. It turns out that if you're at STP, which means standard temperature and pressure, 1 atmosphere, 273 Kelvin, if any gas is at standard temperature and pressure, if you have 1 mole of that gas, it will always occupy 22.4 liters of space. So if I'm at STP and I have 1 mole of oxygen, that 1 mole of oxygen will take up 22.4 liters. The molar volume is 22.4 liters per mole of any gas at STP. So we're going to use that as a conversion factor. So make sure you kind of mark molar volume down somewhere. Because if you have a mole of gas at STP, how much volume does it occupy? 22.4 liters. Okay, so that is very important. From Avogadro's law and from molar volume, we can also get another calculation or another property of a gas that we can calculate. If we want to know the density of the gas, a density of gas is always, what is density anyway? It's always mass divided by volume. Mass divided by volume. The density of a gas can be used to help identify it. So that's something that we're going to be calculating in a few minutes. It's going to be very important for a gas. So the density of gas is mass divided by volume. The units for a gas, because gases occupy so much more space than solids or liquids, won't be grams per milliliter. The units for gas density are typically grams per liter. Grams per liter. Now, let's talk about the density of a gas if you have 1 mole of gas. The density of any gas at STP, okay, so what happens if your gas is at standard temperature and pressure? Well, if you have 1 mole of gas at standard temperature and pressure, you know that you automatically know the molar volume of that gas. For every 1 mole of that compound at STP, it occupies 22.4 liters for every mole of that gas. That's molar volume. And instead of the mass, if you have 1 mole of gas, we can use the molar mass. So what we see here, and the molar mass, remember, comes from the periodic table for gas. So you can look that up on the periodic table. So basically, if you have 1 mole of gas at STP, you can calculate its density. It's the molar mass of the gas divided by the molar volume. Now, why is this important? You can actually rearrange this equation. You can calculate molar mass of a gas. If you have a gas at STP and you know the density of the gas, if you're at STP, you know the molar volume, you can rearrange this equation. You can say that the molar mass of a gas is equal to the density of that gas times its molar volume at standard temperature and pressure. So this equation of density, if you have 1 mole of gas at STP, can be used to calculate the molar mass of your gas. So now we can calculate density or molar mass. Let's look at some example problems. Alright, so the first question here says, calculate the volume of 3.2 moles of oxygen would occupy at STP. So calculate the volume that 3.2 moles of oxygen would occupy at STP. Alright, now we need to calculate volume. We're given moles and we need to calculate volume. And we're at STP. Anytime you ever see that you're at STP, you need to think about what that means. Standard temperature and pressure. Now we have moles given, and we want to find volume. Okay, so that's our unknown. Do we have anything that can convert moles to volume? We don't have an equation to calculate moles to volume. If you look and you can see, do I just have an equation with moles and volume? You don't. But what you do have is you have the conversion factor for molar volume. The volume of any gas at STP is 22.4 liters for every 1 mole. Right? This is a conversion factor. Now we're going to solve this as a conversion. If we have 3.2 moles of a gas at STP, if we know 1 mole of gas at STP is 22.4 liters, can't we just multiply our 3.2 times 22.4 liters? Meaning, if we have 3.2 moles of gas, we know that 1 mole of gas at STP occupies 22.4 liters. So 22.4 times 3.2 equals, what does it equal? I get 71.68 liters, or roughly, 2 significant figures, 72 liters of gas. So when we're at STP, if we're given the moles and we need to find the volume, we can use molar volume as our conversion factor. Converting moles to volume, you use molar volume. Alright, so that's how we're going to use that. Let's go to the next problem, because we've got an a mixture here of density problems and molar volume problems because they're all kind of interrelated. All right, the next problem says calculate the density of nitrogen gas at STP. Okay, we got density. Now, we have two density equations we talked about. We know that density equals mass divided by volume, right? But are we given the mass and are we given the volume of this nitrogen gas? We are not. We also know that density equals molar mass divided by molar volume. And although we're not given molar mass or molar volume, we know what those are. So if we assume we have 1 mole of nitrogen. Now, what is nitrogen? Nitrogen is that's not nitrogen gas. Nitrogen is diatomic. So 1 mole of nitrogen gas N2, can we figure out what the molar mass is? Yeah. Nitrogen's 14 for 1 atom, 14 times 2. The molar mass of N2, nitrogen, is 28 grams per mole. So that's our molar mass. We got that from the periodic table. Same place we're always getting molar masses. And so if we assume we have 1 mole of nitrogen, we know what the molar mass is. We also need the molar volume. We're at STP. So the molar volume of any gas is 22.4 liters for every mole. Notice I've got a mole on top and bottom. Those are going to cancel. What are my density units going to be? Grams over liters. So the density of the gas of nitrogen is going to equal 28.0 divided by 22.4. I get that that's 1.25 grams per liter for nitrogen gas at STP. So basically, we can do this for any gas. If you have any gas at STP on the periodic table, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, which is not a gas, wait a second, neither is chlorine. Let's retract. Nitrogen, oxygen, fluorine, chlorine, helium, hydrogen, what are some other ones? Neon, argon. If you know the molar mass of any of those gases, and you're at STP, you know the molar volume, 22.4, you can calculate the density of any gas. All right? So that's what we just did. Let's look at the next problem. It says, which of the following gases is most dense? All right. Well, we know the density of gas is molar mass divided by molar volume. If we assume all of these gases here are at STP, all the molar volumes are the same. So really, when we're comparing the densities, we're going to look at the gas with the highest molar mass. Let's see. Hydrogen gas, that's 1 times 2. It's about 2 grams per mole. Nitrogen, we just said, was 28 grams per mole. Let's see here. Carbon dioxide, carbon's 12, oxygen's 16. So 16 times 2 is 32 plus 12. Carbon dioxide's 44. And oxygen weighs what? Oxygen is 16 times 2, 32 grams per mole. So I'm giving you the molar masses here. And since they all have the same molar volume, the highest density will be the gas with the highest molar mass, which is carbon dioxide. So carbon dioxide is the most dense. Now, if we put all of these gases together and we layered them by density, the carbon dioxide is more dense than hydrogen. It would sink to the bottom of the gaseous mixture and the hydrogen would float to the top if they didn't mix. All right, so that's the density of that gas. Let's look at the next one. It says, determine the molar mass of a gas if 3.9 grams of the gas is occupied by a volume of 3.52 liters at STP. That should say STP there. Determine the molar mass. So I don't know what the molar mass of a gas is, but I'm given the mass of a gas. That sounds funny. The mass of the gas is 3.94 grams, and we're given the volume. The volume of the gas is 3.52 liters, and we're at STP. Okay. Determine the molar mass of a gas. If the gas occupies, if you're given the mass and the volume, and it's STP. Okay. We did have an equation that we talked about earlier, and we said we could rearrange it to determine the molar mass of a gas, and that was the density equation. So I'm going to go back to the density equation. We said, I'm going to erase here, the density of the gas, of any gas, is the mass divided by volume, but could also be molar mass divided by molar volume. Okay, so we're going to solve our problem here. Are we given the density of the gas? No, we're not given the density of the gas, but we can solve for the density of the gas because we're given mass and volume. So that's what I'm going to do first. I am going to solve for the density of the gas. So density equals mass, 3.94, divided by volume, 3.52. The density of the gas will be, so I'm dividing these two. What is the density? Let's see here. Gotta grab my calculator. I get 1.12 grams per liter. Okay, so that's the density of the gas. Now, I also know that density equals molar mass divided by molar volume. If I don't know what my molar mass is, can I substitute anything else in to calculate that? Well, I just solved for density, and if I assume we're at STP, because we are, then I know my molar volume. So I'm going to erase some here so I can solve. So I have that we solve for density with mass and volume, but density equals molar mass divided by molar volume. If we're solving for molar mass, then molar mass equals density times molar volume. Okay, so molar mass is going to equal the density, which we said was 1.12 grams per liter, times the molar volume. The molar volume of a gas at STP is 22.4 liters per mole. Notice how I have a liters on top and a liters on bottom. Those are going to cancel. So I've got 1.12 times 22.4, and I didn't round before, but I get roughly 25. Is that what I got? Yeah, 25.1. My units are grams over mole. Grams per mole, that's mass per mole, that's our molar mass. So I can solve for molar mass if I know the density and the molar volume. Okay, so this is an example of using that density and molar volume calculation to calculate molar mass. Okay, that'll be the end of this video. And in the next video, we're going to talk about the ideal gas law.